Welcome to this lecture on the distribution of the sample median. Imagine you're a teacher lining up 5 students from shortest to tallest. The student standing exactly in the middle represents the median height. Today, we are going to explore how this middle value behaves when we take random samples from a larger population and why it is such a powerful tool in statistics. To begin our journey, let us understand why the median is so incredibly useful in real life. If a giant suddenly walks into our room of students, the average height shoots up dramatically, but the middle person's height barely changes. This shows that the median is highly resistant to extreme, unusual values, which we call outliers. However, in statistics, every random sample we draw is slightly different, meaning the sample median itself will change from one sample to the next. By studying its distribution, we can predict exactly where the true middle of the entire population is likely to be. Now that we understand why the median is important, let us look at how we find it mathematically. We first take our random sample of data points and sort them in order from smallest to largest. These sorted values are called order statistics because their position depends entirely on their rank. The sample median is the specific order statistic that splits this list perfectly in half. If our sample size is an odd number, there is one exact middle number we can point to. But if it is an even number, there is no single middle. So we must take the average of the two numbers closest to the center. Building on that idea of an odd-sized sample, let us look at its exact mathematical distribution. This formula tells us the probability density of the sample median taking on a specific value x. Conceptually, it calculates the probability of having exactly m values fall below the median and exactly m values fall above it, multiplied by the likelihood of a data point landing exactly on the median itself. The fraction at the front uses factorials to count all the possible ways to arrange these data points. If the original population density is taller at a certain point, the median is naturally more likely to land near that point. Before we move on, let us see this formula in action with a concrete example. Suppose we draw a small random sample of 3 observations from a uniform distribution between 0 and 1. This means every number between 0 and 1 is equally likely to be chosen. We want to find the exact probability distribution of the sample median. Because our sample size is 3, which is an odd number, we can use our exact formula. First, we identify our variables. We set 2m plus 1 equal to 3, which means m equals 1. For our uniform distribution, the probability density function is simply a flat line at 1, and the cumulative distribution is just x. Continuing with our calculation, we now substitute these specific pieces into our odd case median formula. We replace m with 1, the cumulative distribution with x, and the density function with 1. The factorials in the fractions simplify to 3 factorial divided by 1, which is simply 3 into 2 into 1, giving us 6. Multiplying the remaining terms together, we get our final simplified probability curve, 6x into 1 minus x. Physically, if you graph this, it forms an upside-down U shape, peaking exactly at 0.5. This proves that even from completely flat data, the middle value of 3 random picks is highly likely to cluster near the center. Now that we have successfully used this formula, let us understand exactly where it comes from. To find the probability density function of the median, we start with the general formula for the distribution of any single order statistic. This general equation describes the probability distribution for the rth smallest value in a sample of size n. It looks complex, but it simply multiplies the chances of having r-1 values below our target and n-r values above it. To adapt this for our median in an odd-sized sample, we define our total sample size n as 2m plus 1. Continuing our derivation, we need to pinpoint the exact middle position. Since there are m values on either side, the median sits at position r equals m plus 1. We substitute these expressions for n and r into our general formula. The exponent for the values below the median, r minus 1, simplifies perfectly to m. Similarly, the exponent for the values above the median, n minus r, also simplifies to m. The factorials in the denominator become m factorial times m factorial. This mathematical reasoning beautifully yields the exact odd case median formula we used earlier, proving that the median is perfectly balanced with m values on each side. So we have proven how the median behaves for odd samples. This brings us to the case where the sample size is an even number, written as 2m. In this scenario, there are m values in the lower half and m values in the upper half, leaving no single value in the exact center. Therefore, the sample median is defined as the average of the two middle values. To find the exact distribution of this average, we cannot just look at one number. We first need to know how these two middle values behave together by finding their joint probability distribution, which tells us the likelihood of them taking on a specific pair of values simultaneously. Following that logic, here is the mathematical form of that joint probability distribution. This formula gives the likelihood for the two middle values, where x is the lower middle value and y is the upper middle value. Conceptually, it calculates the probability of having m-1 values below x and m-1 values above y, multiplied by the likelihood of the two middle values actually landing on x and y. However, to find the final distribution of the median itself, we would have to use advanced calculus to integrate this joint distribution over all possible pairs of x and y that average out to our median. As you might guess, this exact calculation is incredibly complex. Because that exact calculation for even samples is so messy, statisticians usually rely on a powerful alternative. When we collect a very large amount of data, a beautiful mathematical phenomenon occurs. The distribution of the sample median transforms into a perfect bell curve, regardless of what the original population looked like. This is known as the asymptotic distribution, and it is a special version of the central limit theorem applied specifically to the median. As the sample size grows infinitely large, the sample median clusters tightly around the true population median, giving us a highly reliable estimate without needing complex calculus. Let us look at the mathematical form of this beautiful phenomenon. This formula represents the asymptotic distribution of the sample median. The arrow with a D means converges in distribution, meaning it becomes exactly like the normal distribution, represented by n, as the sample size grows. The 0 means the error between our sample median and the true median shrinks to 0. The fraction represents the asymptotic variance. Notice that the denominator contains the height of the original population's probability curve exactly at the true median. If the original data is highly concentrated at the center, this height is a large number, which makes the overall variance very small, meaning our estimate is highly precise. Now that we have this powerful approximation formula, let us apply it to a real-world scenario. Suppose we are measuring the heights of 100 adult men. We know that the population heights follow a normal distribution with a true mean of mu and a variance of sigma squared. Because 100 is a large number, calculating the exact distribution is too difficult. So we will use our asymptotic formula. First, we identify what is given. For a normal distribution, the true median is exactly the same as the mean. Therefore, we must evaluate the normal probability density function exactly at the center point, which gives us 1 over the square root of 2 pi sigma squared. Continuing with our calculation, we take this peak height of the standard normal bell curve and plug it into the asymptotic variance formula for the median. The formula requires us to square this height and multiply it by 4 in the denominator. When we square the fraction, the square root in the denominator is completely removed. This leaves us with 1 divided by 4 times the quantity 1 over 2 pi sigma squared. We are doing this step by step to see exactly how the variance of the original population influences the variance of our sample median. In this final step, we simplify the complex fraction. Dividing by a fraction is the same as multiplying by its reciprocal, so the 2 pi sigma squared moves up to the top. Dividing by 4 simplifies the expression to pi sigma squared over 2. This is our asymptotic variance constant. To find the actual variance of our sample median, we divide this constant by our sample size n. Physically, this final answer tells us something fascinating. Because pi over 2 is about 1.57, the sample median is about 57% more variable than the sample mean for perfectly normal data. However, if outliers are present, the median remains the safer choice. Let us look at a diagram that visually summarizes the power of this asymptotic distribution. On the horizontal axis, we have the value of the data, with the true population median marked as theta. The wide, light blue curve represents the original population distribution, which is quite spread out. However, look at the tall, dark blue curve. This represents the distribution of your sample median as you collect a large amount of data. It becomes a very tight, narrow bell curve centered exactly on the true population median. This narrowing effect is exactly why large sample sizes give us such high confidence in our statistical estimates. To wrap up our lecture, let us review the most important ideas we have covered. First, the sample median is an incredibly robust tool because it is highly resistant to extreme outliers. Second, we saw that while odd-sized samples have a clean, exact mathematical formula, even-sized samples require complex joint probabilities. Third, and most importantly, we learned that for large samples, the central limit theorem takes over, and the median's distribution beautifully converges to a tight, normal bell curve. You have now covered the full mathematical foundation of the sample median, giving you the tools to handle messy, real-world data with confidence.